phase velocity of a wave is the rate at which the wave propagates in some medium. This is a velocity at which the phase of any one frequency component of the wave travels. For such component, any given phase of the wave, for example, let's say crest, will appear to travel at the same velocity. The phase velocity is given in terms of wavelength, that is the lambda, and the time period capital T. Therefore, we can write phase velocity as small v subscript p is equal to lambda over capital T. That is equal to Vp is equal to nu lambda. In terms of the wave's angular frequency omega, which specifies angular change per unit of time, and wave number or the angular wave number, that is small k, which represents the proportionality between the angular frequency omega and the linear speed, that is speed of propagation Vp, we can write Vp is equal to omega upon 2 pi into 2 pi upon k. Just get Vp is equal to omega upon k, as nu is equal to omega upon 2 pi and lambda is equal to 2 pi upon k. So this is the equation for the phase velocity. To understand where this equation comes from, consider a basic cosine wave y of xt is equal to a cos of kx minus omega t. After time t, the source has produced omega t upon 2 pi, that is equal to ft oscillations. After the same time, the initial wavefront has propagated away from the source through space to the distance small x to fit the same number of oscillations. Therefore, we can write kx is equal to omega t. Thus, the propagation velocity v is equal to x upon t is nothing but omega upon k. The wave would have to propagate faster when higher frequency oscillations are distributed less densely in space unless the wavelength is reduced shorter. Formally, we can write phi is equal to kx minus omega t. The phase velocity would always greater than the velocity of the light. According to the theory of relativity, the velocity of any particle v should always be less than the velocity of light, that is c. Thus, this result is unexpected and meaningless. Thus, phase velocity can be written as Vp is equal to omega upon k, where omega is equal to 2 pi nu is angular frequency and k is equal to 2 pi upon lambda is propagation constant. As Vp is equal to nu lambda and E is equal to h nu and P is equal to h upon lambda, so we can write, rearranging these equations, we can write Vp is equal to capital E upon h into h upon p, so that is equal to E upon p. So Vp is equal to capital E upon small p. When the atomic particle velocity is non-relativistic, that is the total energy E is equal to mc square and momentum P is equal to mv, therefore the phase velocity of de Broglie wave associated with the particle can be written as Vp is equal to capital E upon small p, that is equal to mc square upon mv. So by simplifying this equation, we can write phase velocity Vp is equal to c square upon v. So in this equation, Vp is a phase velocity and c is a speed of light and small v is a velocity of the particle. Now let's see when the atomic particle velocity is relativistic. The total energy is equal to under root of m0 square c raised to 4 plus p square c square, where m0 is the rest mass of the particle. Therefore, the phase velocity of de Broglie wave associated with the particle can be written as Vp is equal to capital E upon p. So by simply putting the value of E in this equation, m0 square c raised to 4 plus p square c square divided by p square whole bracket raised to half. So after simplification, we can write c in bracket m0 square c square upon p square plus 1 bracket raised to half. That is equal to c in bracket m0 square c square lambda square divided by h square plus 1 raised to half. As p is equal to h upon lambda, so by simply putting the value of p in this equation, we get this modified form. In the above equation, the term m0 square c square lambda square divided by h square is always a positive quantity. The phase velocity of de Broglie wave associated with the atomic particle is always greater than the speed of light. So, according to the theory of relativity, it is not possible that the velocity of any particle wave is greater than or equal to the velocity of light. Hence, a harmonic wave of wavelength lambda cannot represent a moving atomic particle. Thus, de Broglie waves cannot be harmonic waves. So, this is very important. The phase velocity of a wave is the rate at which the phase of the wave propagates in space. Therefore, the phase velocity of a single wave is the velocity with which a definite phase point of either crest or trough of the wave propagates in the medium. Therefore, de Broglie wave is associated with every material particle. As particle moves, wave also moves. Therefore, phase velocity gives the speed with which de Broglie wave travels. Consider a particle velocity is equal to v and phase velocity for that particle vp is equal to c square upon v. For a material particle, when speed of particle is very much less than the speed of light, then phase velocity vp is greater than the particle velocity, which is unexpected as v should be equal to the speed of the light. This is all about the phase velocity.